I'll tell you that when it goes around, after it makes its way around. All right, so example 8. It says, let p of x equal this polynomial, find the zeros of the function, and then sketch the graph. Pretty easy. So what's the parent function? The parent function. X to the 4th. So this is a quartic polynomial, yeah? Degree 4 polynomial. What's the leading coefficient? -2. -2. So if you're going to write some of that stuff out using the correct notation like from above, you would say here that n is equal to 4, and a sub 4 then becomes the leading what? Coefficient. If you look back at the definition of the polynomial, if the degree is 4n, then a sub 4 is the leading coefficient, which is -2, and because it's less than 0, we know that the graph what? Opens down. Oh yeah, good, because it's an even degree polynomial. It has the same end behavior. You could say it opens down on both sides. Very good. But remember, in general, the leading coefficient, whether it's an even or odd degree, tells you which end behavior, the right or the left. It tells you the right end behavior. So we know that for sure it's going to exit the bottom. Now, as Ms. Martin just said, because it's an even degree polynomial, it's going to have the same end behavior, so it also enters the bottom. But the leading coefficient always gives you the exit behavior, the right end behavior. Okay? I like the fact that it opens down. So that's on the ends. But locally, it's going to do hopefully some pretty interesting things. What is the maximum number of x-intercepts this thing could have? The maximum number of x-intercepts? 4. Good. Could it have fewer than that? Yeah. Could it have just 3? No. X-intercepts. Yeah, it could have just 3. One of them could bounce or something like that. Could it have just 2 x-intercepts? Yes. Could it have just 1 x-intercept? Yes. Could it have 0 x-intercepts? Yes, right? So the x-intercepts can be any number less than or equal to the degree. If it's an even function, even degree function, we can go all the way down to 0. If it's an odd degree function, we have to stop at 1 because it's guaranteed to have at least 1. Now let's talk about relative extrema. What's the maximum number of relative extrema it could have? 3. And then the next fewest it could have is what? 1. Can it have -1? No. So only 3 or 1. That's the one, the relative extrema, that has to be an odd number occurring in pairs. All right, so to figure out what it looks like, we want to find the x-intercepts, the zeros. And to do that, we need to set the polynomial expression equal to what? We're trying to find the zeros, so we set it equal to 0. Now, that's something you will have to show me on any kind of quiz or free response type question. You're solving now a conditional equation. You don't have to put p of x there anymore. You're setting p of x equal to 0. Now, once we set it equal to 0, we solve it by attempting to what? Factor it. Good. And the first rule of factoring is to find a common factor. Yeah. And so what is the common factor all the way through? X squared for sure. Now, yeah, I would recommend if your leading coefficient is negative to go ahead and factor out the negative as well. It'll just make it a little bit easier. And when we do that, then it's going to change all the signs, and we're going to have 2 fewer x's. So we're left with 2x squared plus x minus 3. And it's still equal to 0. We're in the habit now of keeping that equal 0 all the way down. And we're not done, right? Now we focus on anything else that's still factorable. We have a quadratic trinomial. So we bring down the negative x squared. And this is one of those fun varieties, yeah? Where the leading coefficient is not 1. Yay! I love fun stuff. Okay, so this one is actually pretty easy because both the leading coefficient and the constant are both prime numbers. So they only factor one way. So you know that 2x squared has to be a 2x and an x. And then the 3 has got to either be a 3, 1 or a 1, 3. That's it. It's one of those two combinations. Show up, there it is. Now because your center has to be a positive 1 sum, the numbers are going to have to be pretty close to each other. So with a little trial and error, you will realize that it's got to be a 3 here and a 1 there. So you get a 3x on the inside and a 2x on the outside. I need to subtract them and get a positive 1. So the larger product has to be positive. So there it is. Hey, no problem. You're welcome anytime. If you want to just stay here, we can do that too. All right, let's go ahead and list the x-intercepts now. You don't have to physically set each variable factor equal to 0. You can use the factor theorem, which says if you know a root, you know a factor, and if you know a factor, you know a root. So the roots are going to be x equals, from left to right, what? 0. And again, for some reason, that's the one that students tend to overlook because he is kind of hiding in the front, right? There's no parentheses. It's not x minus something. He's just like, yo, I'm here. What's the multiplicity of that one? It's a double root because it's a double factor. It's x times x. It's x squared. So remember, the exponents on the linear factors tell you what the multiplicity of that root is. So graphically, what's it going to do at 0? Bounce. Good. The next root is what? -3/2. Now, that's one that if you think you're going to mess up, that might be one that would be worth setting it equal to 0 and actually bringing the 3 across and dividing through by the 2. What's the multiplicity on that one? It's an M1, so that's going to what? Cross, bounce, or wiggle? Cross. And then the last one, of course, is just 1. I hope we can all agree on that, and it's a multiplicity 1. So that's also a cross. So remember that the sum of the exponents on your linear factors gives you the degree, which turns out to be the exact same thing as the sum of the multiplicities, right? Turns out to be the degree. 2, 3, 4. All right, so now that we have that, and we know the end behavior, we can make not just a sketch, but an awesome sketch. We're going to need a y-axis, and there's one right there. And we're going to need an x-axis. There's one right there. Things are just falling into place. Now the tough part. We have to pick a flavor for our graph. What flavor do you want? I'm going to go to the pastel palette. Gold. Is that the top left? Sure. Okay. Nice. In honor of the Tower of Hanoi, where the monks had 64 golden discs. All right. So let's go ahead and put our x-intercepts on there. 0 and -3/2. That's like -1.5. So if here's -1, here's -2, -3/2 would be right there. And then I got +1, which is going to be right there. So I just put little dots at each of those. Now, here's just kind of a little tip. If you make your dots further apart, it actually makes it a little bit easier to sketch your graph, but it's not required. I like to give you numbers that are near 0 because when you factor it, it makes it easier, but then it also congests or crowds your graph, as you'll see. Okay, so now for the actual graph. I need to then come in from the left, from either the top or bottom. I need to pass through or touch each of those x-intercepts doing the correct thing, and then I need to exit the correct way. So, first things first. Coming in from the left, are we coming in from the top or bottom? Well, we said it comes in from the bottom. Now, here's the thing. When you come in from the bottom, you do not come in curving upward like part of a smile. Polynomials do not do that, okay? Polynomials come in curving like this, okay? Curving down like a frown. So have it doing something like that. If you hold your arms up like this, curving in like you're about to do a pirouette, that's what polynomials do. They're embracing, okay? So they either look like this, that would be top in, top out, and it's part of a smile coming in and going out. In this case, they look like this. They're still embracing, right? They're hugging. So it's coming in as part of a frown, and it's leaving as part of the frown. Now, if your end behaviors are opposite, it looks like this. It's smiling coming in and frowning going out, or it's what? Frowning coming in and smiling going out. It's never this. It's never, watch this, this hurts. It's never, ow, it's never this. It never comes in like this, or this, ow, or that. That's like the Egyptian thing. This is like hugging, right? So it's like this, like this, like this, or like this. Okay, good, good. Some people's end behavior gets a little wacky, and I'm going to be a little bit picky on the end behavior. So, now that I approach -3/2, what do? Do I bounce, cross, or wiggle? I just shoot across. Now I'm going to go ahead and redraw that because now I have a target. It kind of helps to know what you're going to do before you get there. Ah, my hand hit it. Stupid palm. There we go. I like that. Put an arrow on the end. So see how it's coming in, kind of curving downward. We say it's concave down. It's part of a frown. And I just shot straight across there. At 0, what am I doing? Bouncing. Now, the higher you go, the harder it is to make the bounce. So that's why you want to kind of plan ahead. So now I'm just going to kind of turn around, and you still want it to pass the vertical line test. Something like that. I do not care what the X value of the local max is or the Y value of the local max. I'm not going to be looking at that right now. So you can turn around as high as you want to go or wherever you want in between there. But now I'm going to bounce at 0. Now, it's helpful to know what we have to do at 1 because it's so close. We're not going to have a lot of time to readjust. What am I doing at 1? Crossing. So I'm bouncing here, and I'm not going to go up that high at all. And then I'm just going to turn around and cross. And remember, when it crosses, it leaves embracing, right? Hugging. Here is what I see some people in the early stages doing with their end behavior. They're drawing it like this, and then they kind of get wiggly. Every time your graph wiggles, it's accounting for a higher degree polynomial. So this is no longer a 4th degree polynomial. This could be a 6th degree polynomial or an 8th degree polynomial. So have a steady hand. Don't wiggle. And here's the other thing that I don't like. 2 things. Some people have it going straight like that. It doesn't go straight. It curves. It's a polynomial. Okay? And then the last thing, which is the biggest no-no of all, is some people have it doing this. They have it going out like that. That is wrong. Because what that does then is that, again, it makes it a polynomial of higher degree. So watch your end behavior. Be very deliberate. Just think of always the pirouette, okay? That they're curving inwards on both sides, okay? They come in as frowns or smiles, curving inward. So just looking at your end behavior. Good. Don't wiggle. Don't go straight. Have it curving down. Yeah. And once you have it drawn, of course, if you need to, yeah, good. Just kind of come back and redraw it. See how that looks like it's water going, or it's light going into the water, it's refracting? Yeah. So, and then you look like you have a V there. It's not going to be a V. Okay, a V would not be smooth. Remember, it has to be smoothly connected. So what you want to do is do this, and don't go up that high at all. And see how you're making like a soft landing instead of like a, and then you just come up and then like that. That's what you want to do. Make sure, and it's hard, but make sure I could see that this is a smooth landing. Remember, the function is smoothly connected. So it has to curve and then approach the bounce like it's a smooth landing. It can't just go boing like a V, right? Because that would not be smooth. Okay, any questions on that one? We got it? How many local extrema does this one have? Or relative extrema? How many actual does it have? 3, right? It has 2 local maximums, and I don't know which one is bigger than the other. I just drew it with the one on the left taller, one on the right smaller, but it could be the other way around, whatever. We're not going to worry about that. And it has 1 local minimum. Now, we do know the local minimum is what? 0, at x equals 0, because that's the bounce. So we know the actual value of the local min. So that would be like a good multiple choice question. I could say this function has a local minimum of, and then I can have all kinds of answers there. And how would you answer that? You would graph it and then say, oh, local min of 0. Pretty good. Cool. Let's move on. Any questions on 8? Appropriate wait time, sorry. Yeah, so very quickly, it looks like this has made its way around. Here's the rest of the story. This student seemed pleasant the whole year. But when I got this, of course, I was a little bit disturbed. And it turns out that she did something other than this that was not because... Oh, did y'all notice that the monster also looks, too, like he's kind of he's kind of throwing the bird up, you know? Anyway, but there was a triangle in his tail, if you saw that. She hid that. Okay. She did something that was bad, and I'm not sure what it was, but it was bad enough that she got, I don't know if we say deported, but she got sent back to Norway, and she did not finish the second semester at New Braunfels High School. So, and it was not because of that. So I was relieved when she had to go back, but also then I didn't know where she was. Also, so you sleep finally, but still with one eye open. So anyway, I have not since tried to be friends with her on social media. I'm sure she's out there, and I'm sure maybe they let people access Facebook in prison. I don't know. Yeah. So anyway, I did keep it. It is interesting, and still to this day I keep it as evidence. My wife knows exactly where it is, where I keep it. So if anything happens to me that's of a similar nature, here is the evidence, right? So we have a prime suspect. Yeah. Anyway, I don't know. She, like I said, she seemed very pleasant. But sometimes those are the psychopaths. So I don't do that anymore. All right. Example 9. Let h of m. Is that okay? H of m? Sure. H is the name of the function. M is the independent variable. It says to find the roots and then sketch the graph. All right. The roots are also known as the zeros. What's the degree of this polynomial? 3. Let's go ahead and write that down. Are we still using gold? Let's go to burnt orange pumpkin. N is the degree of the polynomial, and it's what? 3. And so what is a sub 3? 1. That's the coefficient of the cubic term. It's 1. It's the leading coefficient. And because it is positive, we know this graph what? Exits the top. The leading coefficient always gives you the exit behavior, the right end behavior. And now because it's an odd degree polynomial, it must enter where? The bottom. It has opposite end behaviors because it's odd degree. Good. So that's an important thing to figure out beforehand. Now to find the roots, we want to set it equal to 0. So m cubed minus 2m squared minus 4m plus 8. And we set it equal to 0. Now I gave you a hint as to how to factor it, and I'm kind of sad that I had to do that, but I haven't showed you the hint yet, so maybe I didn't give you the hint, unless you know how to read. It's there. If you have 4 terms, how would you go about trying to factor it? Factor by grouping. Yeah, factor by grouping. You studied that or reviewed that this year. And because it's written in descending order, it's ready to go. So I'll group these two together, and ooh, look at that. Remember, this is where you have to be careful, because that's not a plus sign, it's a minus sign. You have to include it inside and put a plus sign here. Or, here's another option if you'd rather do this. Or, you put the parenthesis between the number and the negative sign, but you have to do what with the second term? Change its sign. You want to do that? I don't care, so long as you account for the negative. That's doing 2 things in one. So I'm not going to do that. I'm going to give you the option to do that. I will just warn you, don't mess up. Okay, don't mess up. So I'll put a plus sign in there. And now we look for a common factor in the first 2 terms, and we get a what? M squared, factor it out, and we get m minus 2. Now, you know how this works. That m minus 2 is what we're shooting for then in the other term. And when we factor out a negative 4, we do, in fact, get m minus 2. And it's still equal to 0. Now, because we are pre-AP and we've done this already a lot this year, we're going to go straight to the final full-fledged factorization, another alliterative thing. When we factor the m minus 2 out from each term, we're left with a what? We're left with an m squared minus 4. Yeah? Now, m squared minus 4 is a special product, like kaboom, right? It's a good product. You can get all soaps come off of the shower walls with kaboom. This is a different special product. This is a difference of 2 perfect squares, which means it factors into the product of 2 conjugates. Good. So m minus 2 times m plus 2. So again, we did 2 things in one line there, because at this point, we know how to be a little bit more efficient. If you still need to take the extra time to write it as m squared minus 4 times m minus 2 and then go to that line, I get it. Totally understand. Now, oh my goodness, what do you notice? Yeah, I have 2 factors of the same aside from their color differences, right? So we can write that as m minus 2 squared times m plus 2 to the 1st, to the 1th power. And now, still keeping it equal to 0, we can use the factor theorem to list the roots. So m equals what? From left to right? 2, and that's a multiplicity of what? 2. So again, that's how we write it with the parentheses behind it. And the next root is negative 2, and it's a multiplicity of what? 1. And you're done. So if you didn't know the factor theorem and you actually pull the wrong values out, you might say negative 2 has a multiplicity of 2 and positive 2 has a multiplicity of 1. So it's kind of nice to have them be the same. But pull them off correctly. And now that we have those, we are ready to sketch our graph. Let's have some gray axes this time. There's our axes. And how about turquoise for the graph? You all okay with that? I love these new colors. All right. So we're going to plot our x-intercepts first, 2 and negative 2. And so I'm going to go use a little bit more of the x-axis here than I did last time. So there's 1, 2, and 1, 2. And then I'll put my dots there as targets. Hey, look, this function looks like it could have some kind of symmetry, right? Y-axis symmetry maybe, huh? Based upon the roots? Let's go back and review that. Does this function have any symmetry? Is it even, odd, or neither? When you plug in a negative m for the first one, the sign's going to change, right? Because it's an odd exponent. In the second term, when you plug in a negative m, the sign is going to stay the same. So that one changes, that one does not change, so it is neither. It has no symmetry. Okay. Well, it's good to know, because if I drew a graph and it had symmetry, I'd know I'd be wrong. Now what? Bless you. We come in from the left side doing what? From the bottom. And as I approach negative 2, I'm going to what? Cross, bounce, or wiggle? Cross. And then I'm going to bounce at the next one. So here we go. Coming from the bottom, curving downward, cross, and go as high or as low as you want. Let me go a little bit higher here. Come in, curving downward. I'm going to go way up, and then I'm going to come down. And then boing, and do that. Oh, yeah. There it is. That is a beautiful looking cubic polynomial. There's no extra wiggling going on, because every time you throw an extra wiggle in there, you're going to increase the degree by possibly 3, and you don't want to do that. So it does take a little bit of practice, but that's what math requires. That's why it's so beneficial to you. All right, so how many relative extrema does this have? 2, right? Local max or local min. Can we get the exact value of either of those local extremas? Yes. Which one? There's a local minimum of 0 at x equals 2. Good. Remember, the minimum value itself is the y value. So there's a local minimum of 0 at x equals 2. And right now, those are the only mins or maxes we're going to be able to find the value of when they happen to be 0. So I could say where, right? At x equals. You have it curving the other way. Okay. All right. If you're drawing an example of what not to do, I understand. She did that over here too. When she put an X, she said, wrong. It's still curving like that. No, mijo. Look. Like this. Not like this. Not like this. It's not doing. It's doing this. Okay. Not like that. Like this. Okay. Not like this. Okay. Cool. Any questions on that? It takes a little bit of practice. All right, cool. Next one. Number 10. This one's awesome. It says, write A, the general equation of the polynomial function whose only roots are 5m1, negative 1m2, and 2m3. All right, and then write the particular equation. So what does it mean to have a general equation? Well, good question. Let's scroll back up here. This right here is essentially what I'm going to require y'all to do. We're going to call this the general equation in factored form. I'm not going to make you expand your polynomial equations out because that's an activity for Algebra 2. I'm more interested right now in you writing the equations. So what does that mean? That means that you're going to give your function a name. Here it's called f of x. This a in the front is very important. That's going to be your leading coefficient. And then everything else is factored like this. X minus something, X minus something, X minus something, whatever the powers are. So if we scroll back up here to example 8, this right here was factored enough for us to be able to get our roots. But that is not quite in general factored form because this 2 right here is still in there. And if you notice in general factored form, you want it to be just x minus something or x plus something, x minus something or x plus something. So if we put this in general factored form, all I would have to do is factor out a 2 from that factor. And let's see what that would do. I would pull the 2 then out front, and it would be negative 2x squared. And what do I get when I factor a 2 out of a 2x? I'm left with x, right? And what do I get when I factor a 2 out of a 3? I'm left with 3 halves. Good. Times x minus 1. That then could be the general factored form of p of x. And we call it the general factored form because now we can use the factor theorem, right? The factor theorem says if x minus a is a root, then x equals a is a factor. So now you have x minus 1, so 1 is a root. Here you have x plus 3 halves, so negative 3 halves is the root. Okay, so it's kind of like solving it before we actually have to set it equal to 0. The coefficients are 1. And now notice negative 2 is in fact the leading coefficient. So it's a subtle little difference. So that's the general factored form. So now let's move on down here and see if we can write an equation. So this is part A. We do have to give our function a name because it was not given one. So what do you want to call the function? F of x. I love it. It's a solid name. It's a solid name. All right, so how are we going to start? Well, it says general equation. That means we don't really know what a is, so I'm just going to put a in front there. That's the leading coefficient. Now remember, putting a in front makes the allowance for the graph to be stretched vertically, compressed vertically, or of course what? Flipped across the x-axis, which will change or affect the end behavior. Now we can start writing our factors based upon the roots. If 5 is a root, then what's the corresponding factor? X minus 5. And it's to the what power? The 1th power. Good. So our first factor after a is x minus 5 to the 1st. I won't write the first power. All right, the next root is negative 1. So what's the corresponding factor? X plus 1. And what's the exponent on the factor? It's a multiplicity 2 root, so it's a multiplicity 2 factor. So it's squared. So x plus 1 squared. And then the last root is 2, so the corresponding factor is what? X minus 2 cubed. Yeah. Now the factors do not have to be in any particular order other than we typically put the leading coefficient in the front, the constant, and if there is a factor of just x, we typically put it behind the constant. But the other factors that are x plus or minus something, shuffle them around, it doesn't really matter. Commutative property and associative property of multiplication. All right, so that takes care of part A. Now it says, take part A, and now we're switching from alphabetical letters to lowercase i's. So instead of calling it part B, we're calling it part I, whatever. The guy who wrote this is kind of crazy. He doesn't get a lot of sleep because he sleeps with one eye open. Still to this day, 16 years of restlessness. All right, so now it has to pass to the point 0, 10. Now 0, 10 is a specific point that is not on the x-axis. Not on the x-axis. And so how are we going to get the graph to pass through there? Well, all we can do then, because the x-intercepts are pretty much determined, not just where they are, but how we're crossing there, the only way we could force the graph to pass through any point not on the x-axis is by stretching it vertically, compressing it vertically, or flipping it and stretching and compressing it if we have to. That's the only way to do it. So let's go ahead and draw first what our function A from part A might look like, just to kind of get a nice little visual. So a y-axis, an x-axis, and we have 5 over here, and we have 2 right here, and we have negative 1 right there. So we're going to bounce at negative 1, and wiggle at 2. So here's what the graph could look like. It could look like this. Oops, I held it too long. Bounce, wiggle, cross. It could look like that. Or it could look something like this. It could come in from the top, and it could bounce, wiggle, oops, bounce, wiggle, cross. There we go. Those colors are pretty close. That doesn't really help. They project kind of the same. Let me choose a different flavor. Style. How about hairy style? There we go. Oops. Oh, yeah. Just if you live in my house, every time you hear the word styles, that's what you think. That didn't work. Oh, well. Sometimes it's worth just doing over again. No, that didn't work again. How y'all doing? There we go. There we go. Okay. So we have the blue option and the green and the orange option. And the only difference between those is the orange one is going to have a value of A that's what? Positive or negative? It exits the top, so A would have to be positive, yes? So in the orange variety, A has to be greater than 0. And in the blue variety, since the right end behavior is negative, we'd have to have a negative value of A. Now, of course, aside from those two different options, we can stretch or compress this graph vertically to force the values anywhere not on the x-axis through a specific point. Can you see that? I can't really show that, Blake, with Notability, but let's say I wanted the blue graph to pass through this point right here, where my finger is. You can't see it, but maybe I'll put it right there. That's where my finger was. I'll just take that graph and go, and there it is, right? Or if I wanted it to pass through, pick another point. Here, someone here, we'll put, here. This is cool, Notability. We can get people involved. I'll go a little bit thicker. Let's use a different flavor. How about purple? Like, put a point somewhere that's not on the x-axis, just anywhere. There you go, good. A bounce? Oh, that's why I did it wrong. Oh, yeah, I messed up with my colors. Yeah, I messed up with my colors. That I drew it right the first time. Sorry. This is why I messed up. Let's go back. It wiggled at 2, right? So it did that. Oh. Like you did a fine job. Yeah, this is what it wiggled at 2. And then there we go. There we go. My bad. So now this would be A is less than 0. Thank you, Lauren. Yeah, if you're watching the video, it's Lauren. Give Lauren credit. Okay, cool. So there you go. And now to kind of go back to what Blake did, I think Blake put a dot. He put it like somewhere right here. I think it was pretty close. So which graph would we stretch or compress to get it through that purple nurple point? Will we stretch the orange one or the blue one? The orange one. The only difference between the two is the sign. So if we stretch the orange one, we can make it pass through that dot. So that would be a specific value of A. That's a positive number. What? What's the degree of the polynomial? Yeah, if you add up the multiplicities, 3, 4, 5, 6. So it is an even degree polynomial. Yeah. So the end behaviors are the same. It either, as Miss Martin says, opens up or opens down. Okay? If we were to try and get it to pass through, let's say this point right here, which graph would we stretch or compress vertically, the blue or the orange? The blue. And we would have to what? Not stretch it, but compress it. So any point not on the x-axis, we can force our graphs to pass through. Now, how are we going to figure out what the value of A is other than the fact that it's a positive or negative number? Well, we use what's called mathematics. So here we go. If we want it to pass to the point 0, 10, I'm just going to call this one in green the point 0, 10. That's a y-intercept. Doesn't have to be a y-intercept, but that's a nice one. So that's going to be a modification of the light blue one. So here's what you know immediately. You know that because it's going to be a modified light blue one, that A has to be some positive number. And if you wanted to actually draw what it looked like, it would look like that, like that, like that, and maybe like that. So we know A has to be a positive number. So that's what the graph might look like. But how are we going to find it? Again, I said we're going to use math. So here's all you have to do. This is an x and an f of x that satisfies the general factored form that we have, isn't it? So we can think of it as a formula with three unknowns. We have an x, an a, and an f of x. So if we know two of the three unknowns, we could solve for the third. Yeah? So let's go ahead and plug in. So we're going to say that 10, the f of x value, equals a times, and what are we going to plug in for x? A 0. So I'm going to get 0 minus 5, which is negative 5. 0 plus 1 is 1. Squared is 1. And 0 minus 2 is negative 2. What's negative 2 cubed? Negative 8. And so using a 0 or a 1 is helpful because it makes plugging in easy. Okay, so if you want to narrate, we plugged in x equals 0 and f of x equals 10. And now we just solve for a. So we get 10 equals, that gives us 40a, and we divide through by 40, and we get 10/40ths, also known as 1/4. So f of x, we just rewrite it now. We plug it back in up here to part A. It's going to equal 1/4 times x minus 5 times x plus 1 squared. Why do they do that every single day? Oh, is that what it is? It's to remind teachers to take attendance? How did you solve that mystery? Like a faculty member told you, or a student? Someone in another class. Huh, I wonder how they knew. It wasn't like Daphne or Velma, was it? No? That's, okay, so maybe that is. But, that would have been nice if they would have told teachers that that's what that was for, because otherwise it's not a reminder, it's just a random phantom interruption every single day. Okay, so there you go. That's going to be the equation, the particular equation now in factored form of the green graph that we have up there. Yeah, cool. Any questions on that? All right, let's do part II. Part II, let's do that one in red. It says now we want to make it pass through the point 1, negative 4. So let's go up to the graph and see where 1, negative 4 would be. 1 would be somewhere right here in the middle between 0 and 2. Negative 4 would be somewhere, I'm just going to say it's down there. So now that's going to be a modification of the orange graph, right? Which means I know A has to be negative. Now, if you hadn't drawn those scenarios, here's what you would do. You would start at that point right there. Let's just go ahead and get rid of all that other stuff. Let's say we just know it has to pass through there, and we want to know what the sign of A is going to be. Well, we know then that as we go from that point, which is 1, negative 4, as we go to the right towards 2, what do we have to do at 2? Bounce, cross, or wiggle? We got to wiggle. So we come up here, and we do this. And something like that. And then at 5, we have to cross. So then we go up, and we cross. That is all you need to do. If you continue the graph from the point you're supposed to do out to the right-hand side, then you know what the right-hand behavior is, and therefore you know the leading coefficient's got to be negative. That could be helpful, like in a multiple-choice question. And now if you're interested in finishing the graph, as you go out to the left, you got to bounce at negative 1, and so it looks like that. So we want to find that particular equation. We're running out of time, but guess how we're going to do it? We're going to plug in a negative 4 for f of x and a 1 for x. So we get negative 4. We plug it back into the general factored form up there from part A. So we get negative 4 equals a times 1 minus 5 is negative 4. 1 plus 1 is 2. 2 squared is 4. 1 minus 2 is negative 1. Negative 1 cubed is negative 1. So we're plugging back into the exact same thing. And now we solve. Your negative 4's divide out on both sides, but maybe you don't see that right away. Maybe you just call that positive 16a, whatever you want to do. A then would be negative 4/16, which is negative 1/4. Oh, okay. So the graph of the red function has an equation of negative 1/4 times x minus 5 times x plus 1 squared times x minus 2 cubed. And so it turns out that the equation from part I and the equation from part II have graphs that are related to each other. How? They're just reflections of each other. They pass through mirror image y values of each other. They're both a absolute value of 1/4. Okay, we'll stop right there. If you got that idea, you're off to a great start. You got to admit this is kind of fun. It's better than Sudoku. We got 11, 12, 13, and then some summarizing to do. So we should finish pretty easily tomorrow after the quiz. The homeworks will be due on Friday. But we'll have a quiz tomorrow too, so don't let that be a pop quiz. Be something like this. And have a good day.